video, I'm going to continue on to the term 3 part of the focus questions for grade 12 general. We're trying to figure out the correct direction of the field lines. So we know it comes out of the north and into the south, from the north to the south. And actually the first one just happens to be the correct answer. This is actually correct. Very nice. The reason why this one's wrong, because it's going from south to north, that's incorrect. This one here says north to south, and that's fine, coming out of the north, but look, it's saying it's also coming out of the south. That is not correct. Here, what the heck is that supposed to be? That's terrible. Alright, very nice. Question 7, it's talking about the field lines in a bar magnet. Where's the north and the south? So you can see it's coming towards the left, so it's going out that way, out along that way. That's what it's doing. So as we know, it's north to south every time. It's going to go into the south, out, and then into the south. So North Pole is going to be 2 here, South Pole will be 4, so the correct answer is B. Very nice. In this case, a long straight wire, and you're trying to figure out the direction of the magnetic field at point P. So it looks like no calculation needed, so we don't need to worry about the distances and the values, but we can find the direction. We're going to use the right hand grip rule. So you take your right thumb and you point it this way, and your fingers are going to curl around the wire. They're going to curl around the wire, something like this. That's a very nice hand, if I say so myself. That's my thumb, that's my current, and the field is going around like this in that kind of way. If you can put your thumb around it, fingers curling around the wire. Don't know why I'm drawing it again. Maybe I'm just so good at drawing, I want to keep drawing them. And that's my nails. And it's coming out and around. So inside, and let's just get rid of that drawing. I don't want this. What you'll see is that underneath, my fingers are going into the page. I'm going into the page below the wire. And above the wire, I can see my fingernails. I can see my fingers pointing towards me. Remember, dot means out, X means into. Please remember, so many people forget this. So that top of the wire, out of the page, which clearly means at point P, it's going to be out of the page. Anywhere above the wire will be the same, it'll be out. Below will be in. So the current is going right. It's always going to be like this, by the way, if you wanted to memorize that. If it's going left, you can just reverse it. So that's something to think about. If it's going up, we should probably check that. If the current is going upwards, what will happen then? So we're just going to rotate this upwards. That's all I've done. So on the right hand side, I'll keep my X's, and the left hand side, it will be dots. Downwards will be the reverse of this. So that's something to know. If you're not good at figuring out using the grip rule, you can kind of memorize it. I don't like that. I'd rather learn and understand why, but just to help you through your exam, that's something to think about. Now, what's this? The current in a wire is coming straight out of the page, and you're trying to figure out which is the correct direction. So out, I've always given this little trick to my students, so I'll say it again. Out of the page is always CW, counterclockwise. Into the page is always clockwise, CW. I always write this, out and in. So remember that, these two different things. I see out, I know it's going to be counterclockwise. So that's why A is already the correct answer. If I take my thumb and I point it towards me, my fingers are curling around that way. This is counterclockwise, that's how. And that's my fingers again. Very good. B would be for into the page. If it said that, then you would pick B. C and D, these are charges. That's like a proton or an electron. That's not related. This one here, simple electromagnet. How can we increase the strength of this electromagnet? So if we want to increase the strength, we want to have more current, we want to have more number of turns, maybe a higher battery voltage. So decreasing is totally wrong. Increasing the current, yes. Iron yellow cardboard, no. Iron is good, it's a conductor, so we need that so we can get a magnetic field going. What is this? Replace the battery with the lower voltage? No, we want higher voltage. So these are the opposites, so this will be the opposites if you wanted to find. Increasing the coils. Very good. Alright, so which of the following increases the strength of an electromagnet? I kind of just mentioned it, right? Increase the number of turns. That's a current, sorry, but yes, current, turns. Soft iron core, yes, iron is good conductor. Bringing the wires closer together, number of turns, that's very nice. So these are all going to be very good. So the closer the wires, the stronger the field will be between them. So we will pick D, that's nice. Conductor carrying a current directed into the page. So what is happening? Into the page field, what is current? It says out, but then the question says into. So I don't know which one they're expecting us to do, but let's figure it out. So we're trying to find the direction of the force. We'll use the grip rule, not the grip rule, the gun rule. Your thumb, your middle finger. I'm using my right hand with this. You can also use your left hand, but they are reversed. So how many fingers is that? That's 4. My hand looks weird. So in this case, using my right hand, the thumb is the direction of my current, so that'll be my I. And then this one will be my field, B, and this is my force. I call it FBI, like the police, in America, FBI. So what I need to do is find the direction of the force. My I is pointing, well, which one shall I pick? Let's pick into the page. My thumb is going to point away from me, into the page. My B is pointing up, and my force is going to go to the right. My thumb, it's going to be very hard to do that one. My thumb is pointing to the right, and my thumb is pointing into the page, my B is pointing up, and my force is kind of going like that. So I've kind of twisted my hand that way. And that looks like a terrible hand. So yeah, that would be to the right. However, let's say both. Let's say it did ask for out. Let's check what that happens. I is coming out of the page. That's easier for me to do actually, because now I can just point the thumb towards myself, and I'll point my index finger up. And so that's that, and then my middle finger is pointing to the left, and that's my other 2 fingers. So now I am looking at myself right now. That's my current that way. So that would be, in this case, for out of the page, left. Makes sense, it's the opposite of right. So just fine, this question is of course error. So this is either into or out. Hopefully that doesn't happen on your exam. Just pick whichever one you think will be the best. Okay, current carrying wire. Now look, this is parallel. Parallel, straight away I'm going to ignore it. It means nothing. There is no field, force, nothing. Well, there's a field, but there's no force acting because it's LIB sine theta. So sine of 0 or sine of 180 is 0. No need to do anything. Very good. So, I've drawn a line. Let's check this next question out, shall we? Now we have direction of the force on the wire. Okay, so the current is coming down. And the field goes from north to south. So my index finger, I'm going to point it to the right. My thumb is going to point down. So if I was to do that, if I'm going to point this fingers, let me rearrange my hand, it'll be coming towards me. It'll be out of the page. Don't want to try and draw that. My thumb, index finger, and then my middle finger is kind of coming towards me. This is my right hand, and that's kind of how it's looking like towards me. There's other ways to do it, but that's what I've got. Very nice. That's a terrible hand. Okay, let's get some calculations on the go. This is something that might make more sense. You don't need to draw hands. Current carrying wire, current, field, and it's perpendicular, so that's good. And you need to find a distance or length for the force. So of course that's the lib formula. F equals LIB. You're supposed to write sine theta, but sine of 90 is 1. Sine of 90 is 1. I don't really need to write it. So what I'm going to do is go ahead and solve it. The length is what I need. I have my force. That's just 2.1. 2.1. Length, that's x. So multiplied. I, 7.2. Multiplied by 8.9 times 10 to the minus 3 sine 90. You can write it or you can ignore it. I'm just going to ignore it, and if I stick that into my calculator I'll get 33. So that will be 3.3 times 10 one time. So that's 33 times 10 one time. Very good. Don't know why they wrote it like that. Anyway. Okay, what are we trying to do now? Parallel. Oh, I see the word parallel. Parallel means no need to do anything. Directly 0. I'm not even going to read the question. This is 0. A straight wire is this, perpendicular, okay, and we need to find the current in the wire. So we'll just use the same formula. F equals LIB, perpendicular, sine 90, no need to write it. F is what? 8 times 10 to the minus 3. 8, go away, why are you doing this? 8 times 10 to the minus 3 and equals L. Centimeters is not good. I must divide by 100. It must be meters. So that becomes 0.25. Divide that by 100. Multiplied by the current, which is what I need. Multiply that by B, which is the field, which is 5 Teslas. Okay, shift solve, rearrange, whatever you like. You'll get the current to be about 6.4 times 10 to the minus 3 amps. Don't forget the units. Okay. Next, we're moving on to this one here. What's this? Proton has a charge of this and it enters a field with there. What is the magnitude and direction of the force acting on this? So, okay, so first of all, for the magnitude, that's the easy part. The magnitude, we'll just do F equals QVB sine theta. Again, it's perpendicular into the page to the right. They're perpendicular. So I need to find the force. I have a proton, and it's nice they gave us the charge. It's usually written on the front page, but they gave us it in the question. 1.6 times 10 to the minus 19. They might not always give it. If they mention proton or electron, it means that you're kind of expected to know the charge of it, or at least find it on the front page. So I'll multiply that by the speed, 3 times 10 to the 5, multiply that by 2.5, and if I put all that into my calculator, I should get a small number, 1.2 times 10 to the minus 13. So C and D are wrong. Now, is it up or down? Let's find out. My thumb pointing to the right, my index finger is, my middle finger I should say, which is the index finger. Yes, it's index finger pointing into the page, so this is my V. So basically it's the same idea. FB, instead of I replace it with the charge, V. So this way, that's into the page, and I can see that now my middle finger is pointing upwards. So that's how my hand is kind of looking right now. So it's going to point upwards. So I will pick A. If it's an electron, you can just reverse it, or you can just use your left hand. You'll get the same answer. If it was an electron, a minus charge, because it's opposite. This is proton, I'll stick with my right hand. Negative charge, there you go. So this is a minus charge. Direction of the force, so what I can do is directly, I'll just use my left hand because I'm going to just do that trick. My left thumb now is pointing to the right, my middle index finger is pointing down, and I can see that my other finger is kind of pointing towards me. So it's coming out of the page, I would say. So I will say out of the page, out of page. Very good. What is the magnitude of the charge on the particle? So that means we need to find the Q. F equals QVB sine theta. We already know that it is in perpendicular, so no need. We have the force, I believe. Yes, we have. It's 1.8 times 10 to the minus 13 equals Q. I need it. Multiply by the speed. I have it. 7.4 times 10 to the 5. Multiply that by the field. 1.5. Shift, solve, rearrange, whatever. You'll get the charge of 1.6 times 10 to the minus 19. Oh, it happens to be the charge of an electron. Very good. Okay, so now we're going to see in which direction would the current be if the wire was pulled to the right. So we're applying a force to the right. The field is out of the page. The field is out of the page. So that means I'm going to take my force to the right. Field is out of the page. And that way, if I was to do that with my right hand, I am pointing upwards with my thumb. So let me double check. My middle finger pointing to the right, B is out of the page, which means my thumb is pointing up. Now, this is the trick. This is Lenz's law. That means it's going to oppose the change. So my induced field will be the opposite, the induced current. So my thumb is pointing upwards, but that means, due to Lenz's law, it's opposing this change. So it means it's going to be coming downwards. So the correct answer is this one. So when you're asked to find current, you take the opposite. If the wire is being pulled, because if the wire is being pulled, you're going to induce in the opposite direction. This says to the right, so then it's going to be the opposite of that. You can go ahead and use your right hand and get the answer, then just pick the opposite. Or you can use a trick. This might get confusing, but anyway, for Lenz's law, for current, you can use left hand. You can use left hand, only for this. Otherwise, if it's asking for force, use right hand as normal. Use right hand as normal. So FBI or FBV or whatever. So this is good. The direction is being pulled will be my F. The current is going to be, well, obviously the I, and so forth. And the B is the B. So this way, left hand, you'll be able to get it. Okay, so let's move on. What's this one? So now we have this. Which of the following is the correct direction of the induced current, okay, if they're being moved? So there's two different moves, downwards and to the right. First of all, moving the wire to the right, that means, well, nothing's going to happen. It's moving parallel to the field. The field is right, and the current, the wire is being pulled to the right. So A is wrong, B is wrong, and This D is wrong as well. Oh well, we've kind of got the answer already now. But let's make sure we know the current is from Q to P. Let me go ahead and try that. So which way is it going? So Q to P means the current is supposed to be coming out this way. Let's verify. Now, I'm looking for I. What does that mean? I can use my left hand. So let's use my left hand. I'm going to take my index finger. I'm going to point it to the right. I'm going to take my index finger, point it to the right. My force is going downwards because it moved downwards, so my middle finger will be pointing downwards. If I do that, I can see that my thumb is facing me. My other two fingers are in there somewhere. And my thumb is facing me this way. This happens to be Q to P, so that is correct. So I found for current, I just directly used my left hand. And if you've forgotten the left hand, just to remind you, no need. And this one will be my I. And no, it will be my, yes, it will be my, this will be my B, this will be my F. Middle finger is my F, FBI, so opposite. If you do that, you'll get the answer correct. Very nice. Okay, so there's quite a lot more pages. I'm going to pause this now and start on the next video.